Oh, we are live. Theoretically, it is so hot here. We're doing a problem from the IMO, in my opinion, the International Mathematical Olympiad. That's harder to say than I thought. And it's problem number 5 from the 1997 flavor version. It was requested by somebody, Reshma Chandra, I think it was, the fellow who's saying thank you so much for my request. So you're welcome. Anyway, let me give you a little bit of a background. First of all, if you're tuning in on this after the live stream, welcome, and you have the advantage of being able to skip ahead and look at different parts and see them all over again, because there are so many parts to this problem, and when we get to them, I will, once this is posted afterwards after the live stream, when we get to them, I'll timestamp them, because if you really want to follow this problem, you're going to want to go over and look over parts and then try parts yourself and all that. So let's roll. And I got to tell you, I'm going to let you know right now here, there's a lot to this. And I'm going to do as much as I can right now, but I also want to go and sit in a cold tub of water. So what we're going to do first is we will do we're going to hit this thing with a broad bat. And as we do that, I will write down all of my assumptions. And this not going to seem like there's a whole lot. And we're going to solve this. We'll probably solve this whole thing in about 10 minutes. Then you're going to go, really? That's all there is to it? But then we'll go back and look at the assumptions and go, but we were assuming this. And then that branches off and to a whole lot of stuff. We got to, the devil is in the details, as they say. Let me stop talking about it. Let's get rolling with this. So hello, I see somebody watching. Thanks for watching. And if you have any questions or whatever, or you just want to pipe in with something, the chat's right there. So awesome. Go ahead. Anyway, that's 3 minutes of me not even getting anywhere. So let me get to the whiteboard. Let's see here. I got to make sure that you can see it all. Can you hear me okay? Yes. Thanks a lot for accepting my request. You're there, Reshmi Chandra. Yes. You're welcome. Awesome. So what are we looking at? We're looking at, I'm going to just change the size of this. So we have got a bunch of letters. A to the b squared, and that equals b to the power of a. And we want to show, hang on here, and we want to show, find the values a and b, okay, and everything's integers, okay, integers, and a and b are greater than or equal to 1. Find all the values for which this works. And I went and I graphed this with making a x and b y and all that, and you get a nice little curve. And the idea is you want to find, that's graphing it over the reals, but you want to find integers that make this a and this b work. Okay, so you know what? So the first thing I'm going to do, and I'm going to write little assumptions here, assume, and these are the things that we're going to have to go and mess with eventually. I'm going to assume that that a is greater than or equal to b. Okay, and often you can do that because the problem is symmetrical. Here it's not. Okay, but this is something we're gonna have to deal with eventually. But I'm gonna assume that A is equal to B. And then you know what? I'm actually going to, as I said, take a broad hammer at this. I'm going to eliminate any knowledge that we have about exponents. So I'm just going to say A to the power of n equals B to the power of m. Because that's what we've got. We've got A to the power of something equals B to the power of something. Okay. And then I'm going to do that so that I can take the nth root of both sides. Okay. And so then we end up with A equals B to the power of m over n. And then I'm going to make a substitution here. I'm going to say m over n. I'm just going to call that k. What's it? Can you guys see this? Biro's made for tablets. Okay, go away. Okay, so finally, all of that is just to rewrite this problem looking like this. Remember, k is m over m over n, and m is just a. So really, we've got m equals b to the power of k, but we're not even going to go there yet. Let's tackle this from here. And so here's our next assumption. I'm just going to assume that k is an integer, is an element of, what is it, z? Not just an integer, but a positive integer. Okay, so positive integer. I should have brought water. Okay. Good evening. Hello, Chad. And Gene Editor, I see you a lot commenting on my stuff. You're my biggest fan. Or one of them anyway. Diehards. Good evening. Yes, it's good morning for me, but yes, I know it's good evening on the other side of the planet. So now let's go. I've actually got notes on this here. I should check them out, but let's see how far I get without them. Okay, so let's do a little bit of substituting. Okay, so we've got A equals B to the power of K. And let me bigify this here. Okay, A equals B to the power of K. And actually, you know what? Now we can substitute. So we've got, let's see here. So for A, if A is B to the power of K, then we've got over here, we've got on that side of the equal sign, we've got B to the power of A, which is B to the power of K. And what have we got over here? We got B to the power of K. Okay, that's our A, and I'll put this in parentheses. And we've got B to the power of K to the power of B squared. And you know, and this is, again, you look at this and you're going, am I simplifying this? Well, let's am I just making it worse? Let's get rid of the parentheses. You got to be really careful with these power towers that you're doing everything in the right order. All right, so that's B to the power of B, BK. Okay, so now we've got what looks like a common base, and so now we can make these equivalent. Okay, sorry, that should be yeah. This nope. Already, I can see I'm making a mistake here. KB squared. What did I do wrong? B to the power, because this is not going to end up being what I want it to be. I end up with B squared equals B. Which is a possible solution. This one, I think I can do this without notes. I think I can do the simple part without notes, and then I just go nuts. Okay. So I'm going to look at my notes. Okay. A equals BK. BK to the power of yeah. See, there you go. I made the exact mistake that I said I told everybody don't do. Don't multiply these. Don't multiply those. Just you're going to keep that as b to the power of k. If you go multiplying them, you're nuts. Okay, so that's got to stay up there. Okay, so now let's get rid of these bases. And then we've got k b squared equals b to the power of k. And remember, we're assuming everything is integers and that k is an integer. And quite frankly, if k isn't an integer, we're all doomed. So this is a good thing to assume, because otherwise this problem becomes hugely messy. If I had this on a test or an exam or something like that, this is how I would start it. I would go, well, I sure hope k is an integer, and then I would work it through, and then I'd hit those assumptions. Okay, so now we've got. I did it again. Look at this. It's like I'm. The k needs to be up here. Okay, so now let's kb squared equals b to the power of k. Okay. Got to deal with that little 2. And the way we're going to deal with that 2 is we're going to multiply that. That's what we're going to bring down. So that's going to turn into 2kb. I think that's what we're. No, hang on. Oh, yeah. I got notes right in front of me. It's just so hot. My apologies to everybody for. Why is this? This is why I edit everything so much. After I'm looking right at my notes. I'm going to start again, and we'll have to just redo this whole thing here. Okay, so this we're right up to here. Okay, I'm just going to copy off of my notes. I'm so hot I can hardly think. That's the problem. Okay, so a is b to the power of k. Okay, so that means that b to the power of k, that's your a. Okay. B to the power of k. We're going up here, ab squared. Okay. To the power of b squared. There's mistakes in my notes. That's the problem. The power of b squared equals b to the power of k. All right. Yeah, there's a problem with my notes, and that's what's messing me up here. Okay, so then we end up with b to the power of kb squared equals b to the power of k, and that's exactly what we wanted, isn't it? Kb squared equals kb squared equals k. That's the problem. Okay, that's where I messed up. No, I didn't, because that's b to the power of k. Okay. I don't think I can keep doing this. Sorry. Okay, so let's do this. This is here's what it is. K equals, let's divide everything. How many listeners have I lost? You see that we're dividing everything by b squared over here. So then we end up with k equals b to the power of k minus 2. Okay, so this is what's going to make us very happy. Okay. I know this is mind-boggling. Yeah. But so here's what it is. I had it all right, and then I started to second guess myself. Like, if you saw the that thing I did the other day with the that that silly integration problem where I'm just moving stuff around, and at the very last minute, after I'd even uploaded it to YouTube, I go, oh, wait a minute. No, there's supposed to be a negative sign here. So I went and I put in the negative sign as an overlay. You can see it's edited in. And then somebody points out, that shouldn't be there. It's like, oh. So then after it's up on YouTube and it's already running on YouTube, then I have to go and I blur it out. And this is the thing. You ever do this where you're writing a test and you go, oh, no, I need to change it. And then you go and you change it and it's wrong now. Okay, K equals B to the K to the 2. So now we're going to try, we can put, I guess we'll put this in our assumptions down here. We're going to try various values for K, and let's see what we get. So first of all, let's try K equals, I assume that K is a positive. What would happen if K was 0, even though that's against our assumption? Then we'd have 0 equals B to the 0 minus 2, B to the negative 2. And so then B would have to be 0. And that goes against our initial allowed assumptions. So that goes against the constraint. So we know that K can't be 0. Okay? So just get that out of the way. In fact, I'm just going to even erase it. Okay. But at least that way we deal a little bit with our assumptions as we're going along here. Okay. So let's try this case. We're going to try this case by case. Since we're assuming it's integer, we're going to try K equals 1. So K equals B to the power of 1 minus 2. And okay, we still have a problem, don't we? So, well, actually not too bad. So that would mean that 1 equals B to the negative 1. So 1 equals 1 over B. So that would give us B equals 1. And we go back to our original problem. I mean, that works. So then we have A to the 1 squared equals 1 to the A. So 1 to the A is just going to be 1. So 1 squared, this is really trivial here. So A to the 1 equals 1. So what must A be? A has got to be equal to 1. So there this is actually a solution. A solution. So we've proved that there's at least one solution. And you go into something like this, you don't even know if there's a solution. The assumptions here are myriad. Okay. We were assuming also that there is a solution. We were assuming that we can find the solution, because sometimes there's no solution, but then you want to prove that there's no solution. And sometimes there's an infinite number of solutions, and you want to be able to characterize them all by some sort of equation. And sometimes you have a finite number of solutions, which is going to turn out that we have here, and you want to be able to prove that you have them all. And sometimes you get something in the case of there is a solution, but it's somewhere after A has to be between 10 to the 193 and 10 to the 3000. You get things like this, and it's just so even not finding the solution ends up being fun. It ends up being something. But we found a solution. We found a solution. So let me clear off some of this. Dead wood here. So that's K equals 1. So I'm going to remove that because I want to try to keep a lot of this up on the screen here. So we found one solution. So let's do a little bit of happy. Let's do a little happy dance. Okay. Now let's try. What did we do? We did K equals 1. Let's try K equals 2. K equals 2. So then we end up with 2 equals B to the power of 2 minus 2, which is 0. Now, just between you and me and the lamppost, nothing in the integer world, you got to be really careful about saying nothing or never or whatever, right? But we're not going to find an integer such that b to the power of 0 is b to the power of 0 is 2. So we get to wipe out k equals 2. Let's try k equals 3. Okay, k equals 3. Okay, so then we've got 3 equals b to the 3 minus 2, which is 1. That's easy to solve. B equals 3. That's a nice B. Will that get us anywhere? Let's try it. So we've got a to the power of 3 to the power of 2 equals 3 to the power of a. What'll make that work? Well, a to the power of 9 equals, that's a 9. Okay, equals 3 to the power of a. Did we connect a and b? Oh, yeah, we did. A equals b to the k. So a equals b 3 to the 3. So that's even easy. We don't have to go here. So a equals 27. So is that a solution? 27 with a is 27 and b is 3. Um, 27 3. Let's try that. So 27 to the power of 3 to the power of 2. So that's 27 power of 9 is equal to something. And then we got b to the power of a. 3 to the 27. This, I mean, how do we check this without like popping into a calculator? This is how my mind works. This is what my mind looks like, folks. All this. I was doing some tutoring. I was teaching some kids, really smart pair of twins, high school physics. I was tutoring. I'd come into their mom's office once or twice a week or something like that, and work with them on their physics. And these guys were key and they were really good. And one time I stood back and I looked at everything on the board, and it was just like, whoa, it's all over the place. And of course, and they're taking pictures with their cell phones. And I don't know, they got some scholarship or something. So maybe they have to get smart kids to be tutored by me because they're the only ones that can follow what I do. So let's erase all of this, and let's just keep now. Hello, short person. It looks like me. Yeah, I'm streaming. You need something?
I was wondering if I could use computer, but it's obvious.
Not at this time. Yeah. Okay. I don't think I'm gonna be too much longer because I'm pretty hot, pretty sweaty. I'm having trouble thinking straight. Okay, that's my daughter. Anyway, where are we at here? Okay, so yeah. So let's find. Can we do this without actually doing this? This is what we want to test. 3 to the power of 27, right? And let me just check here. This is ridiculously huge. Anything to the power of 0 is 1, yeah. Well, except how about 0 to the power of 0? Yeah, that's okay. So we've got so here we've got 3 to the power of 3 to the power of 3. But let's just leave the 9 there. Let's not break that down anymore. And over here, we've got 3 to the power of, what's 27? 3 to the power of 3. Is that right? So there's a bunch of 3's. And here's a 9. So this ends up being 3 to the power of 9. I have no idea. It's right. I'm sorry. I hope you see what I'm trying to do. Okay. How is that for hand waving? Hope you see what I'm trying to do. Rather than multiply all these out, hey? Because you've got 27 all to this horrible stuff. Try to break it down into 3's, because it's just all a bunch of 3's. Figure out how many 3's you've got. Break it all down to 3 to the power of something. Here's what it is. That 27 to the power of 9, 27 to the power of 9 equals 3 to the power of 3 to the power of 9. And there you go. There's your 27 up there. And so it becomes 3 to the power of 27. Okay, so all of that goes to show, yeah, we have a solution here. Yay, solution. 27, comma 3. All right, let's move on. We've just about, because I looked ahead, we just about found all the solutions. And then where it gets fun is dealing with all of those. It doesn't need to be here one least little bit. What are those little zeros? Where's everybody from? Who am I talking to? Because somebody said good evening. Tell me what part of the planet you're all on, and I'll look at it in a minute and make some comments. What did we do? Was that b to the power of 3? I don't even remember what that was. Somebody tell me, what did I just do? Was that, well, sorry, what was my K? See if you're all paying attention. What K did I just use? Oh, India. Yeah, I got a lot of people from India. Oh, thank you. Somebody was helping me out up here, because I'm so, yes. Beautiful. Left side. Thank you for helping. I gotta check the comments. Yeah. Okay. We did K to the power of 3. Okay. Let's try K to the power. Let's try K equals 4. K equals 4. Yes. Okay. So K equals 4. So 4 equals b to the power of 4 minus 2. B squared. Okay. 2 solutions for that. B could be plus or minus 2, but we're just dealing with positive integers, and that's an assumption we're allowed to make. That's a constraint that was given to us at the beginning. So I should say equals. So b equals 2. Okay, so now we've got b equals 2. We got to figure out what a is. But a is b to the power of k, which is 2 to the power of 4, which is 16. So run that through. Let's see. So if a is 16, we got 16 to the power of 2 to the power of 2. Okay, because that's my a to the b squared, right? Yeah. And b is 2 to the power of a, 2 to the 16, 16 to the power of 2 to the power of 2. I'll leave it to you to prove that that's right, to check that solution, but that is a solution. I hereby bequeath that is a solution. So 16, comma 2. Awesome. Okay, now let's go with k equals 4, k equals 5. Got to learn how to count too. The important prerequisite of all this is counting, being able to count. But we're racking up solutions. And the thing is, here's the thing that should be in your head now. It's like, okay, how long are we going to be doing this? Like, are we going? is there an infinite number of solutions? And if so, are we going to be able to find a pattern that we can then establish? So k equals 5. We're going to try that case next. So we get 5. Oh, look, I got a line here. 5 equals b to the k minus 2. So it's 5 minus 2. B cubed. We're not going to get any sort of b out of that. Let's try k equals 6. 6 equals b to the 4th. No. K equals 7. 7 equals b to the 5th. Okay, and you can see that this is going up. As k gets larger, we're not going to get another b out of this, and I won't take the time to prove that because I'm hoping that it just feels right. Okay, you could prove that graphically, or we could prove it with induction, but there'll be enough induction down the road, and we're going to stop there. So because k stops, it all stops making sense when k is 5. We don't have to. That's our proof that we have all of the solutions right here, and that's it. Those are all the solutions. And as I said, apart from the fact that I rambled a lot, the first part only takes a few minutes. I totally got to grab some water. I got cold water. So talk amongst yourselves. I'll be right back. Okay. Oh, it's so good, cold water. Let me just check to see if you're all still there. The meat lies in the proof itself. So you had promised me a chess match a few months ago. Still up for it? Yes, we could stream it. We could stream it. I'll post a. We'll plan it. I'm not doing it now, but we'll post a. Hi, what's up? I'm streaming. I'm talking to people here, and they're watching my math. I went to get some water because it's cold. Okay, which state am I? Are you talking to me? Which state? Oh, such as yeah. So yeah, we will. I'll post a link. I'll figure out a link, and then we'll post it, and we can stream it if you want, or what have you. Okay, so. Let's just touch on one of these assumptions here. We were assuming that A is greater than or equal to B, right? And that assumption worked out. What happens if we go and we not assume it? So if we not assume it, but we're still assuming that k is a positive integer. Okay, so that means I'm going to erase all of this stuff here. Going to erase a whole bunch of stuff. Okay, and Okay. Because to complete this, we have to follow our assumptions now. And what happens is they end up branching off. And we could spend the next, you see those two assumptions? We could spend the next, unless there's another one that I haven't thought of that I assume that it's an important thing to do too, is realize what you're assuming, because that's not always clear either. realize what you're assuming. Let's do this. So let's just try. Yep. Sorry, you're going to have to talk because I can't hear. I'm going to go, I don't know, probably another 10 minutes.
You said you're going to be done soon, like 5 minutes.
Yeah, I know. I'm going to have to finish up soon. People are looking for my attention. Okay, so let's assume that B is greater than or equal to A. I mean, and at one point it is equal to A, so we can actually get away with that. Okay, in which case, instead of before we had A equals B to the K, we won't have that now because remember K is a positive integer, so we're going to have B equals A to the K, and let's see where that gets us. So now we've got A to the K squared equals A to the K to the A. Okay, so this too, I can bring that down into here. So now we've got A to the 2K equals A to the K A. All right. Now we've got that common base. So now we have A to the 2K. That's that. Equals K A. Now let's divide everything by A. Divided by A. And we end up with A to the 2K minus 1 equals K. And then now we go through this whole same thing again. Okay, we're going to start with various Ks. If we, fun thing here is if K equals 1, I won't work through it all, but if K equals 1, we get that 1, 1 solution. So that's actually kind of cool, okay? Because that's part of this, the B and the A being the same. Okay, but let's try K equals 2. Then we get A to the 4 minus 1 equals 2. So A cubed equals 2. Oh, that doesn't do us any good. Let's try K equals 3. Then we get A to the 3 times 2 is 6 minus 5. 5 equals 3. And then we are in a same situation that, well, not same. We were in a similar situation that we were previously when we had K equals 5. Okay, so that means that this assumption is wrong and this assumption is correct. Okay, and now you know what? I'm just going to get started on this Z plus thing here. And I don't think we're going to finish this, but I will try to complete it at some point because it should leave you all hanging. So let's get rid of a bunch of stuff. Okay. All right. So we're good. We're good with A being bigger than B now. That's a fair assumption. So I've circled it, put little happy faces by it, and that's good. Okay. So now let's I want to show some, forget what we know about A and B. We know that A equals B to the power of K, where K is some rational number. I'm going to have to go pretty soon. where K is some rational number, but we still have to establish that K is an integer. Okay, so here's where I'm going to go with this. let's consider the prime factorization of A, which I know sounds really silly because we're dealing with really small numbers. But so I mean, let's pretend that we don't know that we don't know what A is yet, and so that let's just make up some numbers here. So let's say the prime factorization of A equals 2, and we'll say 2 squared, okay? And we haven't figured out how many 3's there are in there yet, okay? So B, okay, is going to have to equal, B is going to have a 2 in it, okay? And the number of 2's in it, it's going to have, first of all, it's going to have an even number of 2's because these are all integers. So we could have like 2 to the 3 halves, okay? Because B to the 3 halves, because then we would have B equals, I'm sorry, folks, I'm getting so tired. I think I'm going to stop here because I can hear myself just sort of rambling. Because what I was trying to do is I was trying to simplify something with figures. Here, I'm going to get us started, but then I'm going to sign off. Okay, we need to do a prime factorization of A. So forget using numbers as examples. So A is some string of primes. P1, P2, P3, all the way up to times P the nth. Okay? And going to get us started here. And we don't know, I mean, and we're listing all of the primes in P. Okay? And ignore the fact that there's only one. Okay? Because we don't know that yet. And that's got some power. We'll call it alpha 1. And this has got some power. We'll call it alpha 2. This has got some power. We'll call it alpha 3. And this has got some power. We'll call it alpha n. Okay? And that equals B to the power of K. Okay? But so if this is A and B, we'll say B equals all these primes, P1, P2, P3, all the way up to Pn, and we'll say beta 1, beta 2, beta, whoa, that got very big. Okay, get small. Oh, yay. Oh, yay. This is my day. Can I help you? For 10 minutes.
You said that like 10 minutes ago. And you said you were going to be done.
Okay, and this is beta to the power n. Okay, so that's B. Okay, so B to the power of K equals all of these exponents multiplied by K. And that was a beta 3 times K. B to the power n all times K. All right, so what I want you to take home here, is that A and B have got to have, yes, I love drawing with Miro. A and B have got to have the same prime factors. And I was meaning to show this by giving examples of prime factors so that we would have pictures that we could look at. Okay, so which means that we can separate each of these. So we could just pretend, okay, we could just look at each of these prime factors individually. So here's on the A side, that's on the A side, this is on the B side, P to the power of 1, B 1 times K. In fact, we could just make that I. for any individual prime factor, this is going to be the case. Okay, and so then we end up with, well, basically we can take out that common base, right? And we end up with some alpha, so that's some power. You see where it starts to get really abstract. Equals some other power times k. And so k ends up being that ratio, b to the power of I to the power, okay, sorry, the ith b divided by the eighth b. Okay, so what does that do for us? What that does for us is that tells us that in this b, this beta, I got to go soon. Okay, they're all strictly larger or strictly smaller than. Sorry, gang, I'm losing it. This leads, you know what? This leads us to proving that k is an integer, and I really have to go because I'm really, really tired. Thank you for sticking around for this much. I hope that we accomplished something because we at least showed that if we make a couple of assumptions, the problem is really easy to solve. And so you could be actually quite satisfied with that. But then where it starts to get really, really piddly is working on those assumptions. And what I may do is write this all up and post a link to it. May do another video where you're not having me hemming and hawing, and I can put all that out. Was there anything anybody wanted to say? You get an invariant. Yeah, priorities. Dedication. Math first, family second. Until you, oh yeah. Oh, I love these comments. These are, oh, don't be sorry for recommending the problem. It's an awesome problem. Oh, yeah. Some nice problem solving skills. So, the thing I want you to get from this is lay out your assumptions. Okay, make assumptions. Okay, don't be afraid to do that. And then you'll notice that if we assumed a couple of things, the problem kind of fell into our lap. Okay, but then where the detail comes in and going, well, how do I know that k is an integer? And that actually takes up so much time working on that. And then we end up actually moving into mathematical induction where we go, well, this is true for this one and this is true for two. But what about all these other ones? And it is quite detailed. There is actually another video, and maybe I can post a link to it so you can go through it. But he goes through it pretty quickly. And my apologies for not completing it, but we took a good bite out of it, and I hope that helped. I hope that helped you. Are you guys like working on? Are you guys going to be like entering the Olympiad? Is that the plan? What do you?
What's the Olympiad?
It's a math contest. This increases my respect for. Yeah. Can you imagine actually just sitting there and having to do it? And we'll be waiting for that chess match, sir. Yes. I will. We'll figure that out. How we're going to touch base on that. Are you in India? Suchit 25. We're gonna have to do morning for me and evening for you, or the other way around. Somebody just showed up. Just like a wart. They come in after after all the work's done. Yes. Okay. Awesome. Okay. We'll figure out. I'm not sure how we're gonna do this, but I can post a link. Question for you. Do you want to stream it? Do we want to do a live stream where we play chess together? I'm talking to you, Suchit 25. Hey, Shibam. Okay, you know what? Like I send you problem requests. I'm gonna post my email. Right, I'm gonna post my email right here. Yeah, and let's do live stream. We'll figure it out. Here's my email. Adam at mathadam.ca. Okay. So yeah, that would be awesome. Let's do a live stream. We'll do a live stream chess. I mean, I have something going on Twitch as well, but you know what? I just as soon just keep it on this channel. Alrighty. So that's my email. Send me lots of questions. Oh, just a second. Yes, may I help you?
You're almost done.
Yeah, I'm actually seriously almost done. We're saying goodbye. I'm so glad we had this time together. I'm barely at 1300. Go easy on me. Okay. I got to tell you. Do you know what I am? I took a big hit, and the best I've been is about 1100 and something. I'm not a genius at chess. So you, sir, go easy on me. Okay. So send me an email and we'll get in touch and we'll figure out how we're going to do this. Let's do that. He says, "Oh, I know." So go easy on me. Maybe. Hey, anybody who wants to play chess with me, email me. Smooth Keys. Email me, and we'll do some chess. And we'll just do chess if you want, or we can stream it if you want. You just let me know. And if you just don't want to play chess, that's cool. That's cool. And actually, I like, because I've beaten 1300s, right? And those are the ones. Those are the ones that I pay, because I got to pay attention. Because if somebody's a couple of hundred above you, you can't let it slip. You can't just, because I was on the phone with somebody the other day. I was playing a 560 and I was chatting at the same time. You get cocky, and that person beat me because they make a move, or there was. Yeah, or somebody will make a move and they don't even notice that it's checkmate, or that they just about checkmated you. So it's really easy to get sloppy. So it's actually the better ones. It's good to play with somebody who's better than you by a little bit. Thank you. You love my content. I appreciate it. I love doing the content. Okay, yeah, prep hard. It's math. It's worth it. I love it. I don't know. Okay, so I'm gonna sign off. What about making a video about the mathematics of chess? Yeah, you know what? That's interesting. I don't know much about that, but that is something I've thought about, because of course that's what the chess computers. That's what you get with the chess computers. Is they mathematize it, because we always think that chess is this physical game. I moved the little horsey, and then he moves the pawn. The bishop slides along here, right? But imagine now for a second that you've got two chess computers, and they're playing each other, and there's no screens. Well, that's not physical. It's a bunch of ones and zeros. Okay, so there's math. So yeah, that's something for me to look into. That's cool. So listen, email me if you want to play chess. Chess is very complicated. I know. Email me if you want to play chess, and we'll figure out what we're going to do, whether we just play on chess.com or we live stream it. I don't care. It's cool. I love playing chess. I'm going to go. Thank you, people. Thank you so much for hanging out and enjoying this very cool math problem. Thank you. I'm taking a long time to say. She said I'm taking a long time to say goodbye. I know I do that. Okay. So. Thank you. Who's my favorite chess player? Who was that? There's that guy. He's so funny. He's the one that calls the knights horsies. No, that's his thing. There's one guy. What was it? Gotham Chess. He calls them horsies. And then there's the other guy, Eric. Oh no, my queen guy. I like him. Okay, I gotta run. Okay, bye. See y'all.